we're going to talk about how we can utilize another type of dating technique known as absolute dating. So prior to the current understanding we have of radioactivity in elements, we had a lot of different estimates for how old the Earth was. Some people estimated the age of the Earth by looking at the number of lifetimes that are accounted for in the Bible. There's a whole section where they talk about like this person begat this person, begat this person. So they counted back and they said, okay, well, based on the fact that, you know, according to the Bible, these are all the people who then begat other people. If we look at their lifetimes, we can figure out about how long the Earth has existed for. Other people looked at the rate of the cooling rate of iron pellets, because we know that the Earth has an iron core in its interior. So they thought, okay, if we can figure out how quickly iron cools, we can kind of estimate how long the Earth has existed for. They've looked at sedimentation rates and tried to compare, okay, well, if sediment forms at, you know, this many inches per year, we can look at the depth of sediment around the globe and then figure out how old the Earth is from that. Most of these estimates were really not good. Off by typically billions of years. Some were more off than others. Some people think like the Earth is only 6,000 years old. So we know in reality that the Earth is about 4.5 billion years old. And the way in which we determined this was through study of radioactive materials on Earth's surface. So when we do absolute dating, what we're going to do is apply a numerical value to the age of a rock. And the way it works is through looking at something known as a radioactive decay. Before we dive too much into it, we're going to just jump back in our minds to high school chemistry and kind of give ourselves a refresher course on what we would have learned about different types of atomic elements in various forms. So just really briefly, I'm going to give you a little crash course in some basic chemistry concepts. So I'm going to write up here so you guys can see it. Okay, not with that marker, since that's not working very well. Maybe we have a better one over here. Do you see this floor marker will work well? No, so it's not working very well. Oh man. Let's see. Okay, pretty good. All right. So in high school chemistry, you probably spent a lot of time studying something known as the periodic table. And on the periodic table, you have all these boxes, and they are representative of different elements that exist on Earth. And we're going to look today at an example for this element, carbon. So on the periodic table, you would see in the middle of this box a letter, or usually one or two letters, that represent the name of the atom that we're talking about. So in this case, we see a big C, we're talking about carbon. Then you're going to see two numbers in the box. You're going to see a number down here, and you're going to see a number up here. This number in the top right corner is called the atomic number. And this number in the bottom is called the mass number. All right, so they tell you information about that element, in this instance, carbon. The atomic number that's shown in the top right corner of the box is the number of protons that are present in the element. And this is going to be intrinsic for each element. So carbon has 6 protons. Any atom on Earth with 6 protons is carbon. If it has a different number of protons, it's going to be a different element. So that atomic number, the number of protons, determines what element you're talking about. So in this case, we're talking about carbon. Now, atoms themselves are made up of 3 separate subatomic particles: protons, neutrons, and electrons. Protons exist with neutrons in the nucleus of the cell, of the atom, and they have a positive charge. Neutrons have no charge, they're neutral. And then electrons have a negative charge. Electrons exist in orbitals around the nucleus of the atom. They don't exist where the protons and the neutrons exist. When it comes to mass, the subatomic particles have different masses. Protons and neutrons both have a mass equivalent to 1 AMU.
which is just the mass unit we use for describing atomic masses. So protons and neutrons both have a mass of 1. Electrons are so small, we say that their mass is negligible, so they essentially have no mass. So based on the fact that we have these different subatomic particles, we can have atoms of the same element that have some differences to them. Atoms can lose and gain electrons, which would convert them from a stable atom to what we call an ion, depending if they've lost or gained an electron. It wouldn't change the mass of the atom, but it would change the charge. If they lost an electron, they would have a positive charge, because normally the protons and electrons are the same, so their charges cancel out. So if you lose an electron, now you have more positive than negatives, so you'd have a positive charge. If you gain an electron, you have an extra negative, so you'd have a negative charge. That's going to be creating ions. We're not going to be talking about that so much for this class. What we're going to focus on is what happens if we change the mass of this atom. When you change the mass of an atom without changing the identity of the atom, you have created a new isotope. An isotope is going to be atoms of the same element with a different mass. Okay, so based on the fact that I told you that the number of protons determines the identity of the element, and the only thing in the element that has any sort of mass are protons and neutrons, logically it should follow that in order to change the mass of an element or an atom without changing its identity, you need to change the number of neutrons. So for carbon, it exists naturally in 3 states. The first one is called carbon 12, the second is carbon 13, and the third is carbon 14. Carbon 12 is by far the most abundant form of this element, which is why the mass number for carbon is very close to 12, because this mass number is an estimate of all of the total carbon atoms in the universe, what they would weigh on average. So it's a little bit more than 12, because some of them have a mass of 13 and some have a mass of 14, but it's a small percentage, so almost all of them have a mass of 12. There's a little bit that has a higher mass because of these extra neutrons. So we're going to take a look at what this would mean. Carbon 12 has a mass of 12, that's what the 12 in the name means. Carbon 13 has a mass of 13, carbon 14 has a mass of 14. Since they're all carbons, I know automatically they must have 6 protons, because that's the definition of carbon. It's going to have 6 protons, that's its atomic number. If it had 7 protons, it wouldn't be carbon anymore. So based on that and the fact that the only other subatomic particle that has mass are neutrons, we should be able to figure out pretty easily the number of neutrons in each of these atoms. 6 protons plus 6 neutrons will get us a mass of 12. 6 protons plus 7 neutrons will get us a mass of 13. 6 protons plus 8 neutrons would get us a mass of 14. So these isotopes are going to be the same element with a different number of neutrons. Now, when the atoms get really big, as would be the case here, they tend to become unstable. So they demonstrate what we call radioactivity. That means that they're going to break apart naturally over time due to some sort of decay process, either alpha or beta decay or a series of decay reactions. We're not going to delve too much into the specifics of radioactive decay. If you have questions about it, we could talk about it at another time. For the purposes of this course, we just need to know that larger isotopes tend to be unstable and therefore naturally break apart. And when they do break apart, they are transformed into a new substance, and that process is known as radioactive decay. So, radioactive decay itself acts like an atomic clock because it occurs at a rate that is predetermined and it is not influenced by outside factors. So temperature, pressure, none of that matters. Once the rock is formed or once the substance is created, radioactive decay starts, and depending on which isotope you're working with, it's going to happen at a constant rate. So because of that, we can reverse engineer and figure out, well, if I know how much has decayed and I know the rate of decay because it's a constant, then I can figure out how long this decay process has been going on. So when we look at certain rocks or certain substances within the earth, we can see how much of their radioactive material has decayed, and then we can figure out exactly how old they are. Okay? It does not work with every single rock. Primarily, it's going to work with igneous rocks, especially containing a certain crystal called the zircons. It's going to work with some metamorphic rocks. It typically doesn't work for sedimentary rocks, and that again should make sense. Sedimentary rocks are made of pieces of other rocks cemented together, all of which could have a different age. So if you're like looking at a mosaic, you're not looking at, if you're dating how old it is, and you look at any piece within, you're gonna look at the date when that piece was originally created, not when it all got glued together. So it doesn't really work for sedimentary rocks. Now, relative dating techniques that we looked at, they work perfectly for sedimentary rocks, right? We can sequence all those sedimentary layers pretty easily just using those 5 principles we talked about, 6, I guess. And now we can add some information with radioactive decay to help us limit down time frames even more. So I might not know exactly how old the sedimentary rock layer is, but if an igneous intrusion cuts across it, and I know exactly how old the igneous intrusion is, well then I can have a sense of how old the sedimentary rock layer might be, because I know it has to be older than that intrusion. So we can kind of just use it in conjunction with relative dating to get a better sense. All right, so that's kind of the first step in this whole process, and there's a little bit more about that on these slides too. All right, so some terms that we're gonna need to know, some vocabulary terms. First is gonna be decay. Decay is the process through which unstable nuclei in parent isotopes emit subatomic particles and transform into another element known as the daughter isotope. So in the decay reaction, you're starting with a larger unstable atom, and it's going to break down into a smaller, more stable atom. And it can change the identity of the element itself. It usually does. So you're going to start with, like, let's say carbon, and then it's going to transform into its daughter. For carbon-14, its daughter is nitrogen-14. For some others, their daughter is going to vary depending on what you're starting with. And we'll look at an example in a little bit. This does so at a known rate, measured in the lab, so predetermined for you. I'm not going to have you memorize any half-life lengths in this class. They'll be provided for you. Some of them you might start to remember, but I'm not going to ask you to memorize them. I'll provide them for you. Half-life is the amount of time needed for 1/2 of the radioactive parent to decay into daughter isotope. So what this means is that if you have a sample and 1 half-life has passed, half of that original sample will have decayed into daughter. After the passage of a second half-life, half of the remaining amount will decay into daughter, and so on and so forth. So you just get lesser and lesser amounts of parent remaining. Every single isotope has its own specific half-life. So the half-life is just the length of time it takes for half of the isotope to decay. It doesn't matter how much you start with. You start with 1,000,000 atoms, you start with 5 atoms. After 1 half-life, half of it will have transformed into the daughter. All right, so what does this mean for us, and how can we use this in dating actual rocks? This is just an image showing you kind of how this process would occur. At the time that the rock is first formed, we would say it's time 0. The rock has just formed, no half-lives have passed. All of the all of the atoms within the sample are going to be parent isotope. After 1 half-life, half of the atoms have transformed into daughter isotope. After a second half-life, half of the remaining atoms have transformed. So we went from 12 white to 6 and 6 to 9 and 3, and then this should really be like 10 and a half. And 1 and a half. I don't know why this isn't really in the middle. It should really be here. Okay, and these are green. And then after another passage, you're gonna have half of this amount decaying as well. So you'd end up with half of this and half of this. So you'd be left with 3/4 of one and 11.25 of the other. And so on and so forth. Now as time progresses, you're gonna get closer and closer to 0 when it comes to parent isotope. But you're never truly going to get to 0 because you're always dividing by 2, and there's no number you can divide by 2 to get to 0. So you're going to form this type of line that hugs the x-axis. If you were to plot it on a chart like this, it's an asymptote. So it's just going to get really close, and then just going to hug right here at the x-axis for infinity. All right, so you can think of it like sand going through an hourglass. If you look at the amount of sand there is at the top and the bottom, you can figure out how long the hourglass has been running for. Okay. We measure the ratio of sand in the bottom to top, just like we measure the amount of parent and daughter isotope. We know the rate at which the decay occurs. That's the half-life of the isotope, so we can figure out how much time has passed. Again, this graph shows you starting with 100% parent. After 1 half-life, you're down to 50% parent. After 2, you're down to 25. After 3, you're truly down to 12.5, you're just rounded to 13. After 4, you're down to 6.25. 3.125, 1.5625, so on and so forth. Okay, and this is some of the examples of radioactive isotopes that you might see in the work that we do in the lab. So uranium-238 decays into its daughter isotope of lead-206. Its half-life is super long, 4.5 billion years or so. It's effective for dating samples between 10 million to 4.6 billion years old. Uranium-235 decays into lead-207. Its half-life is about 700 million years. Thorium-232 decays to lead-208. Its half-life is about 14 billion years. Rubidium-87 decays into strontium-87, half-life of 4.6 billion years. And then potassium and argon, potassium-40 decays into argon-40. It has a half-life of about 1.3 billion years. You can maybe start to recognize some of the terms here: muscovite, biotite, potassium feldspar. All of these are different silicate minerals. So a lot of these silicate minerals that we find in igneous rocks will have some of these elements embedded in them, so we can use them to date these particular types of rocks. Some metamorphic or igneous rock here as well, and then our zircon crystals, like I mentioned before. All right, so I'm not going to ask you to memorize those, but what's important to take away here is that there are limits to how effective certain isotopes are at dating rocks or other samples of certain ages. They're not all good for using for every age. For example, if you have a really long half-life, you can't really date young objects because there wouldn't have been enough decay for us to really measure or to have an appreciable difference, so we can't date things that are very young. Same thing, if you have a short half-life, we can't date things that are really old because you'll have decayed so much that it will be hard for us to accurately measure how much parent is left, and therefore we wouldn't be able to accurately determine how old the sample is. So there are caps to what each isotope can do. The last one we're going to look at is the one I talked to you about earlier, which is carbon-14. So carbon-14 is a little different in that it is found in organic material, so it's found in living things. You may have heard of carbon dating before. Sometimes it's used in like anthropology when they find like a mummy or something, they use carbon dating, or they find like a wooden table and they use carbon dating to figure out how old it is. The difference is this. Living beings, like us, we take in carbon all the time as part of the building blocks of our bodies. And when we breathe in atmospheric carbon, we're breathing in mostly carbon-12, because that's what most of the carbon on Earth is, but we're also taking in small amounts of carbon-14. So if we look at the ratio of carbon-14 to carbon-12 in a sample that's alive, it's going to be a steady amount, because whatever carbon-14 is decaying, we're just going to replace by taking it back in through our surroundings. Once we die, we're no longer replenishing our carbon-14, so the amount of carbon-14 as compared to carbon-12 will decrease within our bodies or in our tissue because it's not being replaced. So even though carbon-12 is not the daughter isotope of carbon-14, we can use the ratio in the same way that we would use it, a parent-daughter ratio. The daughter of carbon-14 is nitrogen-14, but we can look at the carbon-12 ratio to help us. Because carbon-14 has a relatively short half-life, its half-life is only about 5,730 years, so it's only valid for samples that are less than 70,000 years old. Anything past that age, there would be such a small amount of carbon-14 left that we can't see exactly how much there is. We don't know how long the clock has been ticking. So we know that this is only going to be good for younger objects. 70,000 years might sound old, but we know in the terms of geology that's not old at all. That's pretty short. So not even 100,000 years. So it's going to be much better for like anthropological things. Living things take in both isotopes of carbon. When the organism dies, the clock starts. This method can be validated by cross-checking with other indications of age, like tree rings and other things that we can look at to determine age. So this is how we use carbon-14 or radiocarbon dating. And that's it for the notes. Now I am going to show you guys one more thing before we move on to the little activity for tonight. Does anyone have any questions about radioactive dating? Losing my mind. Any questions? All right, so to do absolute dating, you're going to need to involve some math. And there are some equations that we'll look at tonight that are a little bit more advanced, but they're mostly plug and chug, so you can just use your calculator to solve most of these problems. Sorry, I don't know where the USB drive is here. They like changed this computer. It used to be an all-in-one on the monitor, and now they must have changed it. Alright, so I am going to pull up for you a very easy way that we can work with these types of problems. Now, this is going to be very simplistic, so for some of you, you're going to be like, okay, that's so easy, why is she showing us this? For some of you for whom math is not your strong suit, this method will always work. It's a little bit more tedious, but it will always get you to the right answer, pretty much, so we're going to take a look at it.
Will this be posted on the?
I can post it up, yeah. This is just one example, so I don't know if I'll put this exact one, but I just want to show you a table of this. So we're going to take a look at this table together. Anytime that you're doing a radioactive decay problem in this class and you need to find the age for a sample, you can set up a table like this. And there are some parts of this table that will not change at all because they're true no matter what isotope you're looking at. And then there are other things that will change. So the way in which you can set up this table, you can start with time over here in half-lives. So here we have 0 to 4 half-lives shown. We have the amount of parent isotope in grams, the amount of daughter isotope in grams, the percentage of remaining parent, and then we have time again, but this time in years. So if we were to set up a table like this, and we're given a question like, okay, you start with a sample of carbon-14 that has 400 grams, or you start with a sample of an unknown element that has 400 grams of parent element and 0 grams of daughter isotope. Right? How many grams of parent isotope will remain after 3 half-lives? Okay, so that's what the question will ask. We'll go ahead and we'll add it to this chart and we'll figure it out. If we're starting with 400 grams of parent isotope, then that means that when the rock forms at 0 half-lives, we have 400 grams. Every passage of a half-life, we're going to reduce that number by half. So the equation that we would use here is just divide by 2 each step down. We go from 400 to 200 to 100 to 50 to 25. Perfect. Now for daughter isotope, the daughter isotope is what the parent turns into. So we would take whatever amount we see here and subtract it from the previous amount, and that will give us the amount that belongs in this box. Right? We had 400 grams initially, 200 are still parent, that means the remaining 200 have to be daughter. These two numbers should always add up to whatever you started with in your sample. 100 here means we're going to need 300 grams here, 50 here means 350, 25 means 375. Okay, and you can keep this going. If it asks about 9, 10 half-lives, just keep the chart going and you'll figure out the answer at the bottom. This column is never going to change. The remaining amount of parent at 0 half-lives is always going to be 100% parent, or 1 over 1, or just 1. It's all parent. None of it has decayed. After 1 half-life, it's down to 50%. After 2, it's down to 25. After 3, it's down to 12.5, or 1/8. And after 4 half-lives, it's down to 6.25%. And like I told you, after 5, it'll be down to 3.125. It's just half of whatever the previous amount is. Now, just like we figured out here, if half of it is parent, then the other half has to be daughter. If 50% is parent, the other 50% has to be daughter. So if I added a column here like percent daughter, okay, well 0% daughter here, 50% here, 75% here, 87.5% here, 93.75% here. All right, those values do not change, so you could just memorize those. And if you're ever asked, oh, how much parent isotope, what percent of parent isotope would remain after 3 half-lives? 12.5%. Just memorize it. It's going to always be the same. Then lastly, we have our time in years. So time here is shown in a different unit than it is in the beginning. Over there, we're showing time in half-life. Here, we're showing time in years. In this case, it tells us how much time there is in 1 half-life, 15 million years. So for 2 half-lives, we would just have to take 2 times the length of 1 half-life to give us 30 million years, 45 million, 60 million. Okay. So anytime, like I said, you're asked to solve a half-life problem, you could set up a chart like this. You might not need all the columns. If it's just asking you about percent parent, you don't need to set up the rest. If it's only asking you about grams of daughter isotope, maybe you'll need to set up the first two. It's for you to use. It just kind of simplifies the whole process. The math is not hard, right? What math did we do? Division, subtraction, division, subtraction, multiplication. Nothing too advanced. Now there is a more advanced formula that I'm going to show you on tonight's lab, and you can also use that. But if that like stresses you out and you just want to go with this kind of easy elementary way, do whatever works for you. This will not steer you wrong as long as you do it correctly. Any questions? Okay. So then what I'm going to do now is hand out to you the work for tonight. And